Let's talk about partial products. This is a strategy that is used in elementary school to build the foundation that eventually leads up to a standard algorithm. But it's not something a lot of us in secondary are familiar with before we start going. And so a lot of times kids, by the time they get to us in secondary, they feel like they have to do everything with the standard algorithm, but they don't necessarily understand how it works or what all the values really mean. So if we can tie it back to this partial products concept, it should help kiddos calculate a little, not more efficiently, but a little more confidently, right? Because what it does is it breaks it down to where we're really just working with single digit products. We start by writing the numbers in expanded form. 427, 427, 38, 30, and 8. And then we fill this chart in just like a regular multiplication chart. So I'm going to do 30, 3 times 4 is 12. And then I can count zeros, 1, 2, 3. The reason I can just count zeros is because we're maintaining place value, right? Tens, hundreds, thousands. Because 400 times 30 is 12,000. Same thing if we continue across. 30 times 20, 3 times 2 is 6. And then there's 2 zeros, so 100. And then 3 times 7 is 21, but it's tens. 8 times 4, 32. 2 zeros, 3,200. 8 times 2, 16, with 1 0, 160. And 8 times 7 is 56. Now I can write all 6 of these numbers off to the side and add them all together, but it might be a little bit simpler to combine individually. So 12,000 plus the 3,200 is 15, 2, 760, and 266. Then I can write down 760, 266, and add these together. 7, 8, 9, 10, 12, 16, 226 is our final result. It's less efficient, but it makes the calculations simpler. Why do we want to go backwards? Well, it actually connects to upper level mathematics when we start multiplying polynomials. They can do this with the distributive property, right? Over, multiply, and write all this down. But experience at the Algebra 1 and Algebra 2 level tells me that sometimes kids just get swirled around in here and they'll miss a term. But it lines up the same way as the partial products model does. Our hundreds here align with our x squared terms here. And our like terms are always going to stack diagonally the same way. Counting zeros idea works. There was 1, 2, 3 zeros. The same thing is happening here. This is x times x and another x, so we can write x cubed. So it still supports the later mathematics. Very often when we're working with distribution and polynomials, if students are struggling, we'll give them a graphic organizer that looks like this and talk about how to set it up. You can even do factoring that way, where you fill in some of the terms and then undo it backwards. So it's not exclusively a backwards thing, right? We're connecting all the way from elementary to upper level mathematics. The more we work with this model, the more we're really kind of representing what we do if we're working in our head or estimating because we've already developed some fluency, right? I can set up 10 and 6 with 20 and 6, and then I've got 200, 60, 120, 36. So that's 180, 200, 380 plus 36, 11, 416. If I'm good at 25s, I could do 10, 6, 25, and 1, right? I can build this any way I want to as I get more and more fluent with the process. Similarly with 80 and 2, all times 4, 320, and 8 is 328. It's much more like what goes on in our heads, but on paper and organized in a way that we can talk to students about what's going on. Well, what about decimals? When we multiply using the standard algorithm, right, we ignore the decimal anyway. We keep track of the fact that there are 2 decimal places. And then when we get finished, we take our values and we just put the decimal back in there where it went. I can do the same thing with partial products, or I can honor and discuss the place value while we're actually working. And the counting zeros and decimal places kind of works the same way. So in this first box, 10 times 3 is 30. 6 times 3 is 18. I'm going to go ahead and write down 48. 10 times 1 is 10. I've already got my 0 in there, but this came back 1 decimal place. We're dividing that 10 back off, so that one goes here. 6 times 1 is 6. Divide the tenths, so 1.6. 10 times 4 is 40, but now this is hundredths, so we're dividing by 100. And 6 times 4 is 24, again hundredths, so we divide by 100. 0.64, and I'm going to add 48, 1.6. I'm going to put the 0.0 here just so I know I've kept it lined up. And 0.64, 4, 12, 10, 50, and then I just keep my decimal place in there. So if I want to track the decimals all the way through, I can, and then it makes sense how we ended up where we're at. Try these. Pause real quick, and then I'll let you work it, and then I'll show you an example. So when we work these out, with the decimal place value included up here at the top, just like we did before. If I want to ignore those decimals, right, I'm just going to pretend this isn't here. This is now 675. 675. What I really did was multiply by 100 because that's 75 hundredths. Multiply that through, work it just like normal, but then at the end we have to divide that 100 back out. So this moves our decimal over and we end up with the exact same value. Either way, we've got to track it. Whichever one makes the most sense to you and your students is fine. And then same thing over here. I just added these rows to show the calculation all in one place. I hope this helps.